Day 14 of 75, and today we're doing the problem set that separates people who use Go strings from people who actually understand them. Strings and hashing. 3 canonical interview problems: anagram detection, minimum window substring, and duplicate finding, and every one of them hides a trap. You'll reach for sort when a map is faster, or loop over bytes when you needed runes, and your cafe test case quietly breaks. By the end of 5 minutes, you'll know exactly which tool to grab and why. Let's go. First, the mental model. A Go string is an immutable slice of bytes, not characters, bytes. When you write for I equals 0, I lens, I++, you're walking raw bytes. When you write for I R equals range S, Go decodes UTF-8 and hands you runes, where a rune is just an alias for int 32. For ASCII, A through Z, digits, plain English, 1 byte equals 1 character. So the byte loop is correct and about twice as fast. The moment Unicode shows up, that assumption is a bug waiting to happen. Let me prove it. Take cafe. That A is 2 bytes in UTF-8. If you build a byte frequency map and compare cafe against ASF, your byte counts can match even when the strings aren't true anagrams, or mismatch when they are, because you're counting half characters. Switch to 4_ R equals range S and A map, rune, int, and now you're counting real characters. Correct every time. Rule of thumb: ASCII guaranteed input, use bytes for speed. Anything else, range over runes. Now group anagrams, the sort trap. The obvious move: sort each string's characters and use the sorted string as a key. That's O n log n per word. But for lowercase ASCII, you don't need sorting at all. Declare a 26-byte array, increment count C, for each character, then turn that fixed array into a key with string count, smiley face. Arrays in Go are comparable by value, so string arr, smiley face, gives you a cheap, hashable key in O n, no sort, no allocation games. Map of string to string, append each word under its frequency signature, done. Benchmark it, and the array key version pulls clearly ahead as input grows. Onto the heavyweight, minimum window substring. Find the smallest slice of S that contains every character of T. 2 maps and 2 pointers. Map 1 holds T's character frequencies, your target. Map 2 tracks the current window. Expand the right pointer, decrement the needed count for each character you absorb. When the window covers all of T, stop growing and start shrinking from the left, recording the smallest valid window as you go. The whole thing is O n, because each pointer only moves forward. Every character is visited at most twice. The detail people miss: keeping the map lean. When you shrink and a character's count drops to 0, don't leave a dead key sitting there. The idiom is window C. If window C equals 0, delete window C. That keeps your len, window, comparison against len, target, honest. So a simple len, window, equals len, target, check tells you the window is complete. No counters to desync, no off by 1. Decrement, delete the 0, compare lengths. And the duplicate finder bonus, because it shows the third key type. For pure lowercase ASCII, skip the map entirely. Use a bit mask. A uint32 has 32 bits, you only need 26. Set a bit with scene equals 1C. Check it with scene and 1C. 0 allocations, blazing fast. For full Unicode, fall back to map. Rune, struct. The empty struct value costs 0 bytes, so it's a pure set. 3 key types: sorted string, fixed array, bit mask, each trading correctness, speed, and simplicity. Decision table to lock it in. Tiny n where clarity wins, sort, and move on. N grows, or you need real character counts. Reach for a map. ASCII only, and you want raw speed, bit mask, or 26-byte array. Day 14 done. The takeaway: in Go, hashing problems are really key design problems. Pick the key, and the algorithm falls out. Subscribe for day 15.
you.